So again, let's just realize where we are, right? In terms of the material. So we moved into the world of magnetism, and we started building the foundation. Every time when you move into a new world, you need to build the foundation. Basically, you need to present all fundamental laws, fundamental equations, right? And then based on this foundation, you should be able to describe any phenomena. And that's what we did in the world of electricity. First, we presented all possible ways of finding electric field, and then we presented electric force. And that is the foundation. You don't need anything else in order to describe almost. Right. We will see what is still missing, but it will be later. So that's what we need in order to describe almost any electrical phenomena in the world of electricity. So now we're trying to do exactly the same in the world of magnetism. So right now we are still in the process of presenting all possible laws which can be used to find magnetic field. Again, these laws are fundamental, right? So it's a part of our foundation. And then once we finish presenting all laws which can be used to find magnetic field, there will be one step left. Present the magnetic force. Once we have always finding magnetic field and magnetic force, that's the foundation. So pretty much right now we are in the process of laying down this foundation. Right, so in a previous class, we presented Biot-Savart law and we practiced that, right? So it's one first method of finding magnetic field. Universal, no limitations, pretty much it can be used in any problem if you want to know magnetic field. And today we're going to present an alternative approach, which can be used to find, again, magnetic field, Ampere's law, right? And that is a law which is part of Maxwell's, or let's say it's an equation which is a part of Maxwell's equations. So after presenting this Ampere's law, we will have two equations from the set of Maxwell's equations, Gauss's law and Ampere's law. And as you know, Maxwell's equations, they form the foundation of the whole electromagnetism. But now we're just laying down foundation of magnetism only, right? Okay, so now let's present Ampere's law. And again, since it is fundamental, universal, timeless, right? So these laws cannot be derived. You remember what we do in this case? We just present it, sort of, tada, let's enjoy it and use it. Because they are written usually based on observations, and we treat them basically as axioms, right? So, and now that's a fundamental law, and again, we will not be able to derive it, right? So we'll just present it and use it. Okay, so it's still chapter 29, all right, and you know what? In the world of magnetism, I'm going to compare these two worlds a lot. World of electricity and world of magnetism, because there are lots of similarities between these two worlds, right? Except for, you remember where the similarity is broken? In the world of magnetism, we don't have magnetic monopoles, right? That's where the similarity is seriously broken, right? Otherwise, lots of similarities. And every time we will, not every time, but quite often, I will be saying, you remember, guys, we had something like this in the world of electricity. Let's introduce similar, or there must be something similar in the world of magnetism. And so this is one of the moments, right? So I can tell you, guys, you remember we had the Gauss's law, right? So which we use to find the electric field, and it has this integral, nice, elegant integral form, right, in order to find electric field. And I can tell you, you know what, I have a gut's feeling that there must be something similar in the world of magnetism. There must be some law which has some integral form which can be used to find magnetic field. Because a lot of similarities, there must be something similar, right? And that similar law is the Ampere's law. Again, it will have integral form, right? But of course, not exactly the same. It will be just similar structure, somewhat similar structure. Okay, so now at this point, nothing else we can say except for present it, discuss it, and start using it, right? Here's the law. So we have, again, you see, an integral form, as I promised. All right, and again, we see we have an integral with a circle in the middle. You remember what does that circle mean? It means integration is done over a something which is closed. In the Gauss's law, it was integration over a closed surface, like a ball, right? A box, I don't know, cube, right? That in that time we integrated over a surface. Here, this integral, in this integral, we integrate over a line. It's a line integral, right? But since we have a circle in the middle, it means we're integrating over a closed loop. For example, circle, closed loop, right? More complicated closed loop. If I take, for example, this piece of wire, charger, right? Connect these ends. Okay, so now we have a complicated closed loop of a complicated shape. So it's a closed loop. So in Ampere's law, we're going to integrate over a closed loop all the time. It's a line integral. Again, it's a strictly speaking, it's a calculus 3. And most of you are not familiar with integrations over a line, over a surface, over a volume. But again, as you noticed after we used Gauss's law, you see, we take those integrals without actually taking them. We just make a few preliminary steps, justify each step, and then we use just basically our high school knowledge, right? But of course, in Calculus 3, you will learn how to handle these integrals. But anyway, so since we integrate over a closed loop, what does that ds? This ds, it's a infinitesimally small section of the loop. Infinitesimally small section of the loop, ds, right? B dot ds. And of course, B is the magnetic field, which most of the time we want to know. And inside of the integral, we have a dot product, scalar product of B and ds. And the same dot product we had in the Gauss's law, right? But back then we had integration over a surface, now integration over a loop, right? And on the right-hand side, we will discuss it deeper. We have our new universal constant mu naught permeability, right? And again, which describes magnetic properties of vacuum, basically, right? And I in, it's the total current within this closed loop. And that closed loop we're going to call an Amperian loop. Yeah, surprise, surprise, right? Like in a Gauss's law, those surfaces were called Gaussian surfaces. Now we're going to introduce every time some closed loops. Of course, we're going to call them Amperian loops, right? So now, a few properties of these Amperian loops. First of all, again, like a Gaussian surfaces, an Amperian loop is your imagination, mathematical concept. You can say, you know what, I want to use, for example, this closed loop for this Ampere's law. Okay, why not? This is universal law, right? Can be applied at any point of the universe, at any moment of time, by anyone, no restrictions. And any closed loop can be used. You will never be wrong, right? So, for example, if somebody tells you that you cannot use that loop, no, from the mathematical point of view, you can use any loop. But again, for each particular problem, of course, you need to pick the best possible loop so that you can solve that particular problem, right? But in general, yeah, you can use any loop. You will never be wrong. It's like, for example, kinematic equations, right? We can use them only when acceleration is constant. So there is significant restriction, right? But here, in terms of loops, no. Grab any loop and you can apply Ampere's law, right? You can apply Ampere's law. So Amperian loop is an imaginary. Any loop can be used again, but the keyword, it must be closed. If your loop is open, no. Right. In that case, it's illegal to use Ampere's law. It just doesn't work. Then on the, as I said, on the right-hand side, we have current, total current. enclosed by your chosen Amperean loop. Once you pick an Amperean loop, of course, some currents will go through that loop, some currents are going to be outside. So we need to count only currents inside of the Amperean loop. It's, again, lots of similarities with Gauss's law, right? In a Gauss's law, we counted all the charges inside of the Gaussian surface. Now we're going to count all currents inside of the Amperean loop. Okay, and now let's just pick some example and see how it all works. So let's assume that we have 3 wires with current. And most of the time we're going to have situations like this when currents are parallel to each other. Okay, not currents, wires. Wires are parallel to each other. Currents can be, of course, in opposite directions or in the same direction. So let's assume that we have this situation of 3 currents. I1 up, I2 down, I3 up. Right? And we want to apply Ampere's law. It's a universal law. Any loop can be used, right? So let's say I pick. No, you know what? Let me say it this way. First of all, before you can start applying Ampere's law, you have to pick an Amperean loop. Without that first step, you wouldn't be able to move any further. Oh, farther, right? It's the same like with Gauss's law. You remember I bugged you about this. What should be our first step before we can start applying, Gauss's law? And I told you we need to pick a Gaussian surface, right? Because in that case, you know over which surface you're going to integrate, and you know which charges are enclosed. Now the same situation, lots of similarities between these 2 laws, right? So first of all, we need to pick an Amperean loop. Right, so let's say I pick this Amperean loop. I don't know, my soul suddenly desires to use this to use this particular loop. Right. Then since we're going to integrate, you see integral of b dot ds. Whenever you integrate over a line, over a loop in this case, right, you have to integrate in a certain direction. Basically, you need to start moving in a certain direction, adding these small contributions. Because you remember what is integration? It's just adding small contributions, right? So, of course, every time you need to start adding all these contributions either in this direction, what is that, clockwise or counterclockwise. Most of the time it doesn't matter, or maybe it matters, we will discuss in a second. But anyway, you need to pick a certain direction. After you choose the path, you need to also choose a direction. And most of the time it's up to you, but of course there is one moment I will mention about that in a minute, right? So let's assume that for this particular case, I pick, if you look from the top, that will be to counterclockwise direction. You see this small arrows, right? That. So pretty much if you look from the top, it will be counterclockwise direction. So I'm going to integrate going that way. And so now let's see again, what does it mean? What does this integral mean? Right? Because again, it's important to understand integration in this situation because we're not going to take integrals, as I told you, right? We're going to make a few preliminary steps, and then since we know the meaning of this integration, we can use our high school knowledge, right? So, all right, so let's assume I start integrating from this point, adding these small contributions. Again, integration, it's just a fancy word for adding small contributions. In this case, contributions of b dot ds, right? So you start from a certain point, and then you complete the loop and get back to the same point, adding this small contribution. So let's start, for example, I want to start from this particular point. So of course, at that point, there is a net magnetic field, right, B. And of course, over there is a small ds. You remember ds, it's a small, infinitesimally small section of the loop. So you have B, you have ds, they are both vectors. You take a dot product, you remember how to do it. B ds times cosine of angle between them. So you will get a number, of course, right? Dot product gives you a number. So let's say you got number, b.ds. Right. Then what next? You move to the next infinitesimally small section ds next to that, right? So next to that, again, there will be small ds. Of course, there will be new value of the magnetic field, maybe slightly different, or maybe not so slightly different from that b. But anyway, there will be magnetic field. Again, you take a dot product b.ds, add this new number to the previous one. Then move to the next step. Again, new ds, new b, again dot product b.ds, add this number to the previous two, and so on. And then you keep doing this, keep moving around this Amperian loop until you get back to the starting point. Again, every time with every step, you keep adding these b.ds. And once you get back to the starting point, that's what effectively this integral is. Once you finished adding, that's the value of that integral. So now, at the right-hand side, enclosed current. Of course, in this case, current I1 and current I2 are within this Amperian loop. So we have to count only those currents. Current I3 outside, foreigner, right? We're not counting that. It's not within the Amperian loop. We're not counting it towards the enclosed current, right? Again, you see, it's similar to Gauss's law, right? But okay, so of course we need to use I1 and I2. But obviously, since current I1 is up and current I2 is down, they cannot go into the Ampere's loop with the into the Ampere's law with the same sign, right? Again, God's feeling, they must have one of these currents must be positive, the other one must be negative, right? Because they have opposite directions. They must enter into that law with different signs, right? So now we need to introduce the rule which can be used, which must be used in order to find the correct sign that must be used with this or that current, right? And that is basically right-hand rule number 2, but applied in a sort of in the opposite direction, or sort of inverted. So how does it work? Once you pick the direction of the Amperian loop, right? In this case, again, from the top, counterclockwise. Then you take again your right hand. Sorry, left-handed people, right? Actually, both of my bosses were left-handed, right? So I don't know exactly. I need to ask them. How did they apply right-hand rule? What was their story? All right. Yeah. So anyway, right-hand rule, and you need to curl. Okay. Let me, for example, use this loop. Let's assume that this is our loop, right? I simplified, right? All right. So take your right hand, and this is our direction, right? And curl your fingers in that direction. All right. So this is our direction of integration. Your fingers and curl in that direction, and then your outstretched thumb gives you a direction for the positive current. So if current flows upward, up, then that current must be positive. If current flows goes down, then that current must be negative. So again, curl your fingers in the direction of integration, in the direction of the Amperian loop, and your outstretched thumb gives you the positive direction for the current. At that time, I don't know, a couple of years ago, when I was creating this slide, I couldn't find any better hand than this creepy hand, right? So in order to demonstrate that that's how this right hand rule is used here, right? Again, you see, curl your fingers in the direction, fingers of the right hand in the direction of integration, and your outstretched thumb gives you positive direction for the current. So in this case, current I1 is positive, I2 is negative. Again, I3, we're not counting, it's outside of the borders, right? So as a result, in this case, I enclosed, you see on the right-hand side, it's I1, okay, plus I1, minus I2. Right? So that's Ampere's law. And before we start looking at examples, right, I will switch to the whiteboard in a second. Again, I want to emphasize on one thing. Again, it's a great law, universal law. Again, timeless, universal, right, and so on. Gorgeous, whatever adjectives you want to use. But where is a trouble? And I ask the same question when we introduce Gauss's law. And the problem is with this law, again, most of the time it is used to find magnetic field. And where is the magnetic field in this law? It is buried inside of the integral. And if you want to find magnetic field, you need to somehow extract it from that sign of integral, right? And extraction can be ridiculously painful if you have some complicated distribution of currents, right? Of course, I'm sure that there are some probably numerical techniques which can be used, right? But in general, if you look at that from just a mathematical point of view, yeah, that can be ridiculously complicated, right? Most of the time will be ridiculously complicated, right? Unless currents, distribution of currents is nice and symmetrical. In that case, Ampere. In that case, usage of Ampere's law is very simple. Second. Okay, everything is fine. And we're going to discuss only those situations where we will have nice symmetrical distribution of current. Oops. Right. And how many types of symmetries we're going to see? In the Gauss's law, basically we had three types of symmetries, right? We had spherical symmetry, right? You remember we integrated over a sphere. Then we had cylindrical symmetry, and then we had planar symmetry. Planar symmetry we didn't touch, right? So basically we discussed spherical and cylindrical. But in these situations, in the case of Ampere's law, there's only one type of symmetry, right? Cylindrical, because our wires all the time are infinitely long, basically, right? So of course, all the wires most of the wires has cylindrical symmetry, right? Cylindrical shape and cylindrical symmetry, right? All right, and here's the question. So you see, there is a these currents. I1, 6 amps, cross. It means it's into the screen. I2, 8 amps, out of the screen. I3, no idea, no direction, no value of the current, nothing. But somebody was nice enough, prepared us to apply Ampere's law. So that somebody who is nice picked an Amperean loop. You see this complicated loop, but it's closed loop, so it can be used. So no troubles with that. And that somebody picked a direction. You remember, we need to know the direction. So you see, in this case, it's a counterclockwise direction, right? And that somebody was so nice that she actually calculated the value of this integral, b dot ds. And the value of that integral is given in terms of mu naught, to simplify calculations, because you realize why. So that value of integral is 7 times mu naught. A, it's just units of amps, right? So 7 times mu naught. So can you calculate the amount, the value of the current I3 and its direction, right? Again, it's all about Ampere's law. So give it a try, and then of course I will discuss. Once you get the idea, it's a straightforward problem. And in the past, I used problems of this type often in among multiple choice questions. Okay, let me pull up the chat to see your answers. It's a conceptual question number 1. I prepared 3 just in case, but it looks like we're not going to get to the other 2. in this case, since we don't have to find magnetic field, so this question, this problem is basically trivial, right? So the value of the left-hand side, the value of integral, basically is known. So now we just need to carefully write down all information about the enclosed currents, right, with proper direction and proper sign, right, which is related to directions, right? So first of all, which currents are enclosed? I1 is out. I1 is outside of our Amperean loop, so we can forget it, ignore it, right? So whatever, right? Then I2 and I3 are our enclosed currents, right? So yeah, we need to count them. Then we need to, of course, make decision which of them is positive, which of them is negative, right? So I2 is definitely positive. It's out of the board. So and you remember right-hand rule you need to apply. So you curl your fingers in the direction of the travel, right? In the direction of integration, right? And your outstretched thumb gives you direction of the positive current. So in this case, all the currents outward, out of the board, are positive. So I2 is positive. But what about I3? We don't have any information. So in order to write this equation properly, okay, Ampere's law, we need to use the same trick which we used already several times, right? You remember what? Since we know that current either out or in, 50% chances of guessing it, let's use the high percentage, right? So let's just assume a current direction, write this law properly, solve for that unknown current, and if our current happens to be positive at the end, great, it's your lucky day, go buy yourself a lottery, right? So it means that that direction that you assumed is the correct direction, and you found just the value of the current. But if your current happens to be negative, bigger deal. Absolute value you found, if you found, for example, minus 2 amps, it means that the value of the current 2 amps, and minus just indicates that your assumption about current direction was wrong. Make a statement, so actual direction is opposite. You solve problem in both cases, right? So let's use that one more time, that trick. All right, so let's assume a current direction of I3. Okay, I need to, again, slides forward. So those are enclosed, that is not enclosed. And so now let's assume that I3 is out of the page. I just want to make that current positive as well, right? Like positive numbers, right? So that's my assumption. As a result, I can write my Ampere's law in this way. So integral of b dot ds, it is equal to 7 mu naught. So the value of integral I wrote on that side, right? And mu times I enclosed, it's this, mu naught, and my enclosed currents, 8 amps positive, I3 assumed to be positive, right? Plus I3. So, and now we just need to solve this equation. So mu naught over there, mu naught over here, of course, mu naught gets cancelled. And just solve it for I3. So obviously I3 is negative 1. So I3 equals minus 1. So, okay, so now we see that the absolute value of the current is 1 amps, current I3. And minus just tells me, okay, I'm bad at guessing, right? So current I3 is actually into the page. Current I3 flows into the page, goes into the page, right? So that's how you see the problem is basically trivial, right? And of course, yeah, it's better to make a statement, right? So, of course, it's easy to come up with many currents, right? Make problem more complicated, right? So, but anyway, once you know the idea, it's very simple. So next, all right. So the answer is C, right? And most of you pick that option. So now next, solenoid. Why do we need solenoid at this point? So now we know all possible ways of finding magnetic fields. So now we can say we are experts in finding magnetic fields, right? Biot-Savart law, Ampere's law, both fundamental, right? So 2 options, piece of cake, right? right? But of course, from the mathematical point of view, it can be really complicated. Now, from now on, we are going to use most of the time, quite often, uniform magnetic field, right? All right, and of course, now the question: which object can give us a uniform magnetic field? So that we can say, let's assume that we have this object. As a result, there is a uniform magnetic field. Like what? Like in the world of electricity, we had a parallel plate capacitor. It's a electrical system which gives us a uniform electric field, uniform electric field inside. Outside electric field 0, inside uniform electric field. So now we need to introduce a similar device in the world of magnetism, and that is the solenoid. What is solenoid? Very simple. So if you take a piece of wire, right, some cylindrical surface, right, and if you start wrapping this wire around that surface, let me make it nice, right? So, okay, so I just built my solenoid, and if you send current through this solenoid, of course, since we have one wire, so of course in each of these loops we're going to have exactly the same current. That is the solenoid. And this object, this solenoid, inside of the solenoid, there is a uniform magnetic field. So now, instead of it's basically the role of the solenoid is similar to the role of a parallel plate capacitor in the world of electricity, right? So that gives us uniform electric field. This object gives us a uniform magnetic field, right? And I borrowed from the stock room several years ago, and I'm not planning to return because I use it quite often. So this is an example of a solenoid. You have several thousand loops, right? Current in, current out, and inside there is a hole, right? So inside of this solenoid, if you stay away from edges, reasonably away, right? So deep inside of the solenoid, magnetic field is going to be uniform. Now let's just conceptually discuss how it happens that magnetic field inside is uniform, and then I will say a few words about the magnetic field strength. So how can we make a solenoid? So of course, first of all, like in my case, I started with the piece of wire, right? So in case of a just piece of wire, let's assume it's a straight one, right? We can easily find magnetic field lines. You remember? Outstretch your thumb in the direction of the current, and your curl fingers are going to give us directions of the magnetic field lines. Magnetic field lines are circles. Now, next step. What if we take this straight piece of wire and bend it in the first circle? Right. First circle. So what will be the structure of the magnetic field lines? It will be something like this, right? And it makes sense. For example, what if we take this point, which is equidistant from both of these currents? Basically, what are you looking at? It's basically cross section of the wire, right? You see, this is wire, and if you look at the cross section, of course, over here current is in one direction. Over here, the bottom current will be, of course, in the opposite direction because we have a loop current flowing in a circle, right? So that's why you have in one this part, it's dot, here it's a cross, right? And if you take this point, for example, equidistant from both wires, right? Of course, contribution from the top wire, of course, contribution to the net magnetic field will be somewhat up. Contribution from the bottom one, from this one, of course, my contribution to the net magnetic field will be somewhat down, right? But the same in strength. So if you add them up, of course, the net magnetic field direction is going to be horizontal. But if you step, for example, up slightly, of course, contribution from the top wire to the magnetic field, net magnetic field will be stronger than from the bottom one. Of course, now magnetic field lines start bending upward somewhat, right? And of course, here at the bottom, so as a result, you will get a picture resembles to this one. Of course, kind of sloppy picture, but good enough, right? So now you see, what if we take another loop and position next to this one, right? And then, of course, these magnetic field lines will be squeezed sort of inside. And then if you position the next loop to the previous two, and then the next loop, and next loop, and next, what if you create a few thousand loops? Of course, you will end up with a picture like this, right? So all these magnetic field lines are now squeezed between these line of loops, right? So, and if you stay reasonably away from the edges, of course, near the edges, magnetic field lines have density is different, right? Densities are different. So, of course, here magnetic field is not uniform, but if you go inside of the solenoid, you see density of lines are approximately the same. So it means that magnetic field is constant. Magnetic field is uniform. It means the same magnitude and the same direction. Then magnetic field just outside of the solenoid is zero. It's a little bit more complicated to describe. I'm not going to talk about that, just to remember. It's like a solenoid. Oh, I mean, just like a capacitor, parallel plate capacitor. Inside electric field is uniform, outside zero. The same here. Inside of the solenoid, magnetic field is uniform, outside is zero. Right? So that is the system which we're going to use to create uniform magnetic field. So now, okay, this is just sort of like a demonstration, right, of these magnetic field lines. So then, next question, of course, what about expression for the magnetic field inside of the solenoid? And that will be a quiz number 5. Right. At some point, I used to discuss this in the lecture, but it's too much from the mathematical point of view to discuss using slides. No, it's too much. Every time I felt like it's not correct, it's not right. So eventually, I started giving this as the take-home quiz. So basically, you need to derive this formula. This is formula which gives us magnetic field strength inside of the solenoid. Mu naught times n. N is a density of loops, right, per unit length, and times I is the current. So you will have to use either this slide, or you can use any book, right, you want, or use internet, whatever. Just I want you to apply Ampere's law to derive this formula, right? You can use any sources, any resources, right? But you have to show a picture. You see the solenoid. Then you need to pick an Amperian loop. In this case, Amperian loop is this rectangle. You see points A, B, C, and D. This rectangle. Then show magnetic field and ds directions, right? So you see. And then evaluate first left-hand side integral. Of course, you'll have to split into 4 integrals because you have 4 pieces of this rectangle. Justify what happens, explain what happens to each of this integral, and then calculate enclosed current, right? And then put them all together in Ampere's law and actually get this formula, right? I will send you by email, and this quiz will be, of course, after the exam, right? Don't worry about this quiz before the exam, right?